Okay, so now we're going to go into a bit more detail about exothermic reactions. We're going to look at a little bit more theory regarding those. So if I keep that theory there, and we're going to use the other side now to talk about some extra theory. So we're talking about exothermic reactions. What you can do is you can plot an energy profile, and you need to be able to plot an energy profile for these reactions, for what happens during these reactions. So an energy profile, you put time on the x-axis, so time most likely in seconds, maybe minutes, but one of those two units is most likely, so stick with seconds. And then on the y-axis you'd have energy, most likely in kilojoules. Maybe that would be in just joules. It doesn't really matter, but key things: time there, energy there. So let's imagine I've got my reaction. I'm doing an exothermic reaction. So let's think of an example of an exothermic reaction. This is an example of an exothermic reaction. So when hydrogen reacts with chlorine to make hydrogen chloride, there is an exothermic reaction, which means the chemicals release energy to the surroundings. So here now I've got my reactants, and these are the products that are being made, and where we said in the previous video the chemicals release energy, so the chemicals lose energy. So let's imagine if I added up all the energy that these reactants had, it came to about that much energy. So before the reaction has started, at the very start of the reaction, so time is very low at this point, that's how much energy the reactants have. So this is the reactant, or the total energy of the reactants. And then we've said by the time the reaction finishes, the chemicals will have lost energy. So by the time it's finished, so way over onto the other side now, in terms of energy, they're going to have far less energy than they did before. So the amount of energy they have has dropped. So this is now total energy of the products. And you can see the products have less energy than the reactants did. Now, in order to get a reaction to work, it doesn't spontaneously occur. So if we add two reactants together, it doesn't always happen. Often you need to put a Bunsen burner underneath or increase the temperature in order to get it to work. And that's because you need the particles to collide with enough energy. So you need to provide, so if you remember the term activation energy, so the activation energy is the minimum energy required for a reaction to occur. So in order to get this reaction working, I need to provide the activation energy. I need to give the reactants enough energy in order for the reaction to occur. So this is what this little part of the energy profile represents, is me giving the reactants some energy in order to get them to be able to make the products. So I'm giving them that minimum energy. So that is an energy profile for an exothermic reaction. Products have less energy than the reactants, and in order to get them to actually react, I need to provide them with some energy, and that energy is the activation energy to get the reaction working. So we can label this type of energy profile, and you need to be able to label it. So if that's the total energy of the reactants and that's the total energy of the products, this gap here we can call the energy change. So that's the energy change. So the difference between the energy of the reactants and the products is the energy change. That's given a symbol. So it's given delta H as a symbol. So delta means there's a symbol which means change, and then H is for heat energy. So change in heat energy. So the energy change we can label there, and then going from here up to the top. So going from the reactants to the top is the activation energy. So the energy required to get the reaction going is that much energy there. So that's the details about exothermic energy profiles. We'll do for endothermic now. It's a lot faster once you do the second version, but hopefully it'll make those things a bit clearer as well. So endothermic energy profile. So there's our theory for endothermic reactions. So things get colder because they're exothermic, the chemicals gain energy. So an energy profile for an endothermic reaction. Same axes, you're going to have time on your x-axis, let's do it in seconds again, and energy on your y-axis in kilojoules. So the chemicals take in energy from the surroundings, the chemicals are gaining energy. So an example, we talked about thermal decomposition earlier, so let's do one of those as an example. Calcium carbonate will thermally decompose. So what happens is that chemical, you put a Bunsen burner underneath it, it'll take in the energy that's being given out by the Bunsen burner, and it will thermally decompose, so it will break down to make calcium oxide and carbon dioxide. So hopefully you can see that these two products are a broken up version of that thing there. So we've got this is our reactant, and these two things are our products. So there's our reactant, and what's happening is it's gaining energy, so it's taking in energy in order to break apart and make these things here. So in terms of our energy profile, if we say this chemical at the start of the reaction has this much energy, so that is the total energy of reactants. And then what happens is, as the reaction goes by and as it gets to finish, the chemicals have taken in energy. So now this is the total energy of the products. So they've taken in energy, they've caused the temperature of the thermometer to decrease, they've caused the beaker to lose energy and decrease in temperature, but the chemicals have taken in that energy. Same as before, in order to get these types of reactions to work, we've got to provide some energy. So we've got to provide the activation energy. So this time it's going to look like that. So again, activation energy, minimum energy required for the reaction to occur. So we can add some more labels to this now, two very important labels. This gap that we've got between the reactants and the products is the energy change. Just given the symbol delta H. So the energy change, and then going from the reactants up to the top is known as the activation energy. So that's the minimum energy the reactants need in order for the reaction to take place. Now if we compare the two energy profiles, so if I put them side by side now, if I can squeeze them in. So exothermic, the energy of the chemicals is dropping, so the energy change is if we say delta H, so the energy change is negative, so you're going to have a negative value because the chemicals are losing energy for exothermic reactions. And then for endothermic reactions, look at delta H in this one, so the energy change is positive. So the chemicals are gaining energy. Those are two key ideas which we'll build on in the next video.